15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us. This is the Space Nuts podcast, episode 220. My name's Andrew Dunkley, your host. Joining me as always is Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hi, Andrew. How are you doing today?
I'm pretty excited this week, Fred.
Oh, really? Did you hit a golf ball or?
Yeah. Yeah, I did that. Not very well. But my audio book has been released as of yesterday.
Ah, very good. Yes, so, I got that milestone.
Yes, the Turanian Enigma is now available as an audio book. So you can download it from your favourite audio book distributor. I know it's on Google. I know it's on Apple. It's not quite on Audible, but it will be. They're just they're a bit slower than the rest to get the ducks lined up. And I think in all there are 43 audio book distributors that are going to carry it. So that's very exciting. So getting the word out. If you, because this is by demand, people asking to get an audio copy. So I decided, all right, I'll do it.
And it
runs at about 5 hours.
Yeah,
5 hours listening time.
Is that the one that when you play, you hear a voice very similar to the one I'm talking to now?
Could be.
Yeah.
Could be. Yeah, but sometimes it won't sound like me because I go into character. Rather than just do a straight read. So I have a bit of fun.
I like the sound of that. This is fantastic. Yeah. Well done.
Yeah. Making up alien voices is very difficult, I might add. Actually hurt my throat a couple of times. It was bizarre. Anyway, it's all there, ready to roll. So if you're interested, you can download it today. Now, Fred, coming up, we're going to be answering audience questions almost exclusively today, although there's one story that's hit the headlines this week that we can't not do, if that makes sense. But we're going to look at the use of lasers in space and some of the issues facing that particular situation, measuring distance in space and why we use terms like parsec. Or light second or things along those lines. A couple of questions about Venus. One is obviously focused on the potential for life on Venus, which has hit the news this week, so we'll talk about that. But there's also a mission headed to Mars, Venus, I should say, which we wanted to discuss. And we talked about the journey of light from the centre of the sun recently. Somebody's brought that one back to haunt us, so we'll have a crack at that, and the effect of binary stars on planets. So plenty to do today. It's a jam-packed program, I must say. But Fred, let's get straight into it with our first question from Evan in Sydney.
Hi, this is Evan from Sydney, Australia. Recently, Fred talked about astronomers using lasers for adaptive optics. I heard a rumour that US astronomers had to get permission from the US spy agencies before turning on their laser for fear of blinding spy satellites. Is this rumour true? What would this do to ability to schedule time on the telescope? And what happens for sudden events like a supernova or a neutron star collision? Does this affect astronomers in Australia? And do Australian astronomers need to get permission not just from spy agencies in the USA, but also in Russia and China? Hey, I really enjoy the show. Space Nuts is first on my podcast list every Friday.
Thank you, Evan. That's lovely. And I forgot to say hello to you, Fred. Really? Hello?
Hello.
I got so excited about my audiobook, I forgot to...
That's all right. Don't worry about that.
Sort of introduce you properly, but here we are.
That's all right.
Now, Evan's brought up some interesting issues and a little bit of cloak and dagger in there as well. Lasers in space, spy agencies, permission. What's all that about?
So the technology that we're talking about here is the use of what are called laser guide stars. And it's all to do with the elimination of the distortion to a star image that is caused by the Earth's atmosphere. And the technology of adaptive optics lets you sense the distorting effect of the atmosphere and compensate for it by using flexible mirrors. The nicest demonstration of this is one that I can't do because it needs a visual aid. But if you get a sheet of paper and look at it, hold it up, that is what the wavefront of the light from a star looks like as it's crossing space. And if you then take your piece of paper, screw it up and flatten it out again, that's what it looks like when it's coming through the atmosphere. It's very, very crinkled. The difference between the bit of paper and the atmosphere is that the crinkling is changing 1,000 times a second in the atmosphere, whereas on your bit of paper, you've just got one sort of snapshot. And so that's what adaptive optics is trying to do, to use flexible mirrors that can essentially reproduce that crinkled waveform and restore it to the perfection of what it would have been like coming through space. And the technology has actually moved on enormously in the last decade or so. And so a number of telescopes use this technique. None of them are in Australia. That's maybe not quite true, because there is an observatory at Mount Stromlo Observatory in Canberra. They have basically a satellite station on the same site, which is operated by EOS, Electro-Optical Systems, who do use lasers for basically satellite ranging. And it may well be that they have adaptive optics systems built into that, but they're looking very much at things in near Earth orbit rather than distant objects. So let me change that and say, for astronomy, there are none used in Australia, because our atmosphere in Australia is not really good enough to eliminate the crinkling of the wavefront by adaptive optics. I did some experiments with a man called John O'Byrne, a professor at Sydney University. This is, let me see, it's 25 years ago we did these, with the Anglo-Australian telescope to look at the possibilities of using adaptive optics on that telescope. And we did some experiments called LIDAR, where you use a laser to try and measure the turbulence in the atmosphere at different heights. The weather wasn't brilliant, so excuse me, we weren't using the best observing time, but there were multiple layers of turbulence above us, above the mountain top. That mountain is 4,000 feet high, or about 1,100 meters. You need to be much higher than that to get rid of some of these turbulent layers. And so in Hawaii and Chile, they are the main places where adaptive optics are used, and in particular where laser guide stars are used. Why do you need a laser? Well, in order to make adaptive optics work, you've got to be able to sense what the wavefront is doing. And you do that by looking at what's called a guide star. And you can do it with real stars. If you've got a star which is near the object of interest, and it's got to be fairly bright, that's the downside. But if you've got that star, then you can use that to sense the wavefront, and that basically will correct the whole image. So the object that you're interested in, which is next door to the star, that will be corrected too. But often there isn't a bright enough star near your object of interest, and that is why these scientists generate an artificial star using a laser, typically to excite sodium atoms at about 90 kilometers above the Earth. Now, the question that Evan made was basically about the problem of hitting something by mistake, and I am not sure about the US. I think he's right that there are times when you cannot use the laser guide star systems in Hawaii. And that is possibly because of US government's use of space for reasons that we might not be told about. I think they get periods when that's prohibited. That is, it's more than a rumor. I've heard this from some of the scientists involved. It's more, especially though, the case that you want to avoid aircraft going through the beam. That's a more typical
yeah.
situation. And so certainly the laser guide stars that the European Southern Observatory uses on its very large telescope down in Chile, they have got aircraft avoidance systems. I think they have sensors that maybe radar. I'm not sure exactly how it works, but they shut down the lasers with an automated aircraft avoidance system when an aircraft is near the beams. I suspect.
So what effect would a laser like that have on an aircraft if it flew through the beam?
It's not powerful enough to penetrate the skin or anything like that. But clearly, it's not the sort of thing that you want pilots of aircraft who are dark adapted in their cockpit with a blinding light hitting their aircraft, and of course reflecting off all the surfaces, the shiny surfaces of the aircraft, which would then find its way into the cockpit. So the last thing you want to do is point a laser at an aeroplane. People sometimes do it and get arrested shortly afterwards. Yes, so you do have to be very careful about it. As I said, Australian observatories don't use that because we don't have the atmospheric conditions that are good enough to make laser guide stars worthwhile.
He's also asked about sudden events like supernovae, neutron star collisions, things like that.
Yes. So if you have I'm not quite sure what he's getting at there, because with a supernova, what you want to see is the supernova, and you don't know where one of those is going to go off, and so that's very much it would be the target of opportunity. If a supernova went off in your field of view, you'd be delighted. Neutron star collisions are rare enough events. And also in deep space, so that usually the light we get from them is fairly weak. But these are what you might call transient events. There are telescopes specifically looking for transient events, and they are going to be very important in the future. We think the transient universe, where things are popping off, getting bright and faint again quickly, like fast radio bursts, which you and I have talked about many times. The transient universe is very much the future of astronomy. It's something we've been getting used to over the last decade. It's, of course, for astronomers, the transient universe now also includes satellite constellations as well, which you have to deal with. Yeah.
For sure. All right. Evan, thanks for your question. Hopefully we filled in some of the blanks, and we appreciate your support. Thanks again. Now, Fred, let's move on to our next question. We don't know who this is from. It came in text form. Hi, Andrew. Hi, Fred. Astronomy enthusiasts use light years to express distance, but professional astronomers use parsecs. When invented in the early 20th century, the parsec was at the centre of popular research, but is that still the case? Or is this just an historical tradition? It seems the parsec is very Earth-centric. It would be meaningless to non-Earth-based astronomers, of which I hope there are many out there. Its only other use is for starships doing the Kessel Run a long time ago in a galaxy far, far away. For that matter, the light year is also Earth-centric, while the light second can be universally described. Would appreciate your thoughts, would have recorded this, but could not find how to turn on the microphone. Please don't mention that last bit. Oops. Sorry.
Sorry. We don't know who it's from.
I love the line about the Kessel Run.
Yeah.
And a very important lesson to learn there: pre-read everything. No, he didn't say that, but anyway. Light years, parsecs, light seconds. Yeah, what's the story?
So, professional astronomers universally use parsecs. So it's not, as you know, that our listener asks, it was at the centre of popular research, but is that still the case? Absolutely. And the reason is the parsec is the only thing we can measure. You cannot measure a light year. It's a derived unit. It's a nice, convenient one to get your head around. So most people can understand light years. but it's not anything you can measure. You can't stand outside with a stopwatch and say, "Oh, it left then. How long is it going to take?" Parsec is the fundamental unit, and yes, it's Earth-centric, but so are we. Maybe if there are any non-Earth-based astronomers, to be honest, there are none in our neighbourhood. But if there are any, then they would use something similar probably for their definition of distance. They would use whatever unit of angle corresponds to a second of arc. They would use that. I should just explain what a parsec is. It's the distance of an object which subtends an angle of 1 second of arc, or for which the radius of the Earth's orbit subtends an angle of 1 second of arc. So if you imagine a triangle with the Sun, the Earth in its extreme position in its orbit as the base of it, and then a very, very long, thin triangle to the star, and that makes a 1 second angle, 1/3600th of the degree, then that star is 1 parsec away. And actually, there aren't any stars that near. Parsec is about 3.2 thereabouts light years.
There you go. All right. Hopefully that's sorted it out. And yes, how long did it take to do the Kessel Run? What was the record?
I don't know. I don't know the answer to that.
Oh dear. I can't remember either. But they did bring it up in a later episode of Star Wars, and he had to correct the claim because somebody got it wrong. It was funny. But yeah, thanks for your question. Hopefully, again, we've managed to come up with a reasonable answer for you. But parsec, still a thing. You're listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson. Let's take a short break now for a word from our sponsor, Namecheap.com. As their slogan says, search and buy domains from Namecheap at the lowest prices. This is the service the team at Bytes.com use to buy and manage our domains, and we're very happy with the service, support and value we receive. Can't recommend them highly enough. Buying the right domain name shouldn't be hard, and with Namecheap, we've found it to be anything but that. Find your dream domain and join over 2 million happy customers when you register with Namecheap. Trusted with over 10 million domains, you'll find you're in safe hands when it comes to turning your website idea into reality. They also have excellent tools to find the right name for you, like their handy search engine. Just type in your desired name, cross your fingers, and press search. If what you were after is already taken, they'll offer up some great alternatives. And if you're looking for some inspiration, try the new website domain name finder Beast Mode and discover thousands of domain names fast. We've found their prices to be excellent, management tools intuitive and easy to use, with excellent customer support should you need it. All in all, a great experience all round if you're looking to pick up a domain name or 2 or 3 or whatever it is you need. To check them out and help support us at the same time, just visit spacenutspodcast.com/namecheap. That's spacenutspodcast.com/namecheap. And Namecheap is one word. You'll be glad you did, and you'll find the URL details in our show notes and our website. Just visit the support page. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Welcome back to the Space Nuts podcast. Andrew Dunkley here with Fred Watson. And thank you to our social media supporters and followers on all sorts of platforms. We love to hear from you. We get cards and messages. Well, not cards, but messages and sometimes some brilliant GIFs on Facebook that people put up about some of the discussions. You can follow us on the official Space Nuts Facebook page, of course. Just do a search for Space Nuts in your Facebook search engine. Or you can join the Space Nuts podcast group on Facebook. And that's a group dedicated to you talking to each other. And quite often people ask questions there that Fred and I have got no idea about. So go to the podcast group and they'll answer it for you. What I love is that everybody's got an idea to put forward when it comes to a complicated question. And it gets some real interesting answers and sometimes a bit of debate, but it's all in good fun and it's well worthwhile. So if you'd like to join the Space Nuts podcast group on Facebook, please do. You'll also find us on YouTube, which is growing in numbers, and our downloads are increasing. Thank you for that. We're on Instagram. We're on Twitter. We're not on any posters. I'm a bit disappointed. We've got to get on, billboards or something. I think that'd be pretty cool, but that's very old school, isn't it? Never mind. Now, Fred, let's go on to our next question. And or do you want to talk about Venus? Because these two questions are dedicated to Venus, but there's a huge news story this week about phosphine having been discovered in the atmosphere of Venus. Should we go there first?
Let's just do that to introduce Venus, because a remarkable discovery announced this week by scientists, some of whom I know, actually. I talked to one of them by email yesterday. He said nobody's asked him about the phosphine on Venus, which is a bit of a shame, because I've spent most of this week talking about phosphine on Venus. But never mind.
Well, the fact is, I'm surprised no one's spoken to him, because every news report I've seen has basically said, oh, there's life on Venus. Of course, being a journalist and knowing how journalism works, they're going with the sexy side of the story. Yeah, they're going with the grab. But I've seen counter arguments saying, hang on a minute, hang on. It's not life. It may be an indicator of the potential for life. So what is it really?
Yeah, so what's been observed is the presence of phosphine in Venus's atmosphere. Phosphine is pH 3, a molecule made of phosphorus and hydrogen. Phosphine's common in the atmospheres of giant planets, but that's because there's lots of hydrogen there. Giant planets are mostly made of hydrogen, and so there's plenty of it to make the chemical from just normal chemical processes. On a rocky planet like Venus, there isn't that prevalence of hydrogen, and so phosphine for quite some time has been held up as a potential biomarker. Now, this predates the discovery that if we found phosphine in the atmosphere of a rocky planet beyond the sun, orbiting another star, we might be able to say that's a biomarker, that there's life there. But that's great, actually, because what this discovery of phosphine on Venus means is that we can actually test that hypothesis, because eventually we'll be able to go there with a spacecraft and take samples of the upper atmosphere of Venus and find out what's in it. But you're absolutely right. The authors of the paper themselves are very cautious in the interpretation of what they found. They have worked very, very hard to find other causes for the appearance of phosphine, natural chemical, geological causes. And they've looked at volcanism, they've looked at the effect of sunlight, they've looked at micrometeorites, they've looked at lightning in Venus's atmosphere. They've looked at all these different aspects that could perhaps cause phosphine to be there, and none of them can make enough phosphine to compare with what they've actually seen. And so life is their last basically the last suggestion for what it might be, but they're still, in themselves, they're still skeptical. But yeah, of course, they know that this is a big discovery. It's one made with the James Clerk Maxwell Telescope in Hawaii. That's where the people who I know work. But followed up with ALMA, the Atacama Large Millimeter Array. And I think there are more observations that can be done with ALMA that might tell us a little bit more about it. But very exciting stuff.
Yeah, very, very exciting. But as the saying goes in journalism, never let the truth get in the way of a good story.
That's right.
That's written on page 1 of your journalist's study manual when you go to university.
Yeah.
It is. It's the very first page, I'm sure. Now, while we're on the subject of Venus, we do have a couple of questions about that particular planet. So let's go to the question first from Will in Phoenix.
Hey, Andrew. Hey, Fred. This is Will from Phoenix again. Thank you for answering my question last week. That was awesome. I have another question about Venus. I'm fascinated by the planet. it's so similar and so different from Earth all at the same time. I've learned that Venus rotates, I think it's backwards, but very, very slowly. And that is very weird, I think, because it's such a large body. And I know that as bodies get larger, they tend to rotate faster because they conserve angular momentum. And I'm wondering why is Venus so slow? Why does it rotate so slowly? I think it even rotates backwards. I don't know if there was like a giant impact or if we have evidence of some other event or series of events, or I don't know. I would love to hear what you guys think. Thanks, Fred. Thanks, Andrew. Love the show.
Okay, thanks, Will. I have a very quick and accurate answer to his question as to why Venus is so slow, and I'm going to hell for this one because she's a blonde.
Yeah. I'm not going to touch that one, Andrew.
I didn't think you would. But I think there'd probably be a more scientific reason why Venus is slow. Is Venus, in fact, slow?
Yeah. So what Will says is absolutely right. So the year on Venus is 224 days, effectively, actually 224.65 days. Excuse me, that's how long Venus takes to rotate once around the sun. But it's, excuse me, the dreaded frog in the throat again there. But its rotation is 243 days. So it rotates on its axis once in 243 days. What that means is it by the time it gets to the end of a day, it's already gone once around the sun. So 224 days for the rotation, 224.65, 243 days, 26 minutes for, 224 days for the revolution around the sun. We've got to get the words right. Revolution is going around the sun. Rotation is the planet spinning on its axis. 224 days to revolve around the sun, 243 days to rotate on its axis. And what that effectively means, exactly as Will said, it's rotating backwards.
Which means if you live there, you're going to get younger.
In your dreams. If you live there, you'll be fried.
Yeah, indeed.
460 degrees Celsius surface temperature. But
so in layman's terms, because I need to talk that way, its year is shorter than its day.
Yes, that's exactly correct. That's not just the layman's terms. That's what the astronomers would say.
That's a scientific answer.
Yeah.
But Will wants to know why.
Yes. So we don't really know. To some extent, there will be a tidal friction effect. That's what happens with the Earth and the Moon. It's the tidal friction between the Earth and the Moon, this effect of gravity acting on both bodies, that have slowed down the Moon's rotation. It was probably spinning quite fast when it was born, but is now rotating once per revolution, which is why we always see the same side pointing towards the Earth. So what you've got is a similar situation with Venus, but it's kind of slightly overshot because the day is now longer than the year. There may have been, as Will says, there may have been impacts. There may have been catastrophic interactions with other planets where planets come close to it in the early history of the solar system. But I think the rotation is really linked to the fact that it is so close to the sun. It's a large body, so the tidal effects of the sun on Venus are going to be significant, and that is probably the bottom line. That's why it's slowed down. Mercury also has peculiar rotation. It's not tidally locked like the Moon is, but it's got a 1.5 to 1 resonance between the rotation and the revolution. The rotation is 58 days, I think. Revolution, if I remember right, is 88 days. So there's another slightly peculiar effect there. A slow rotation. So both these worlds effectively rotate slowly, and as I said, probably due to the effect of the nearby sun slowing them down.
There you go. Thank you, Will. I love the way your brain works. The way you phrase your questions, I think that's fabulous. Do they conserve angular momentum? I mean, how do you think of that stuff? Good grief. You're too clever for me. While we're on the subject of Venus, we know of a mission going there. David wants to know about that.
G'day guys, David here. Just following up on the recent episode involving the Veritas probe that's going to Venus. I just had a thought, wonder whether the difference in the two planets, Earth and Venus, may be due to the impact from Theia and something to do with the energy lost in that collision that perhaps gave us the moon, as they think. Anyway, enjoy the show. Thanks very much, guys. Keep up the good work.
Okay, David. So he's wanting to find out whether or not a collision issue could be a differential between the planets. And where is Veritas up to at the moment?
It's still a proposal. It's a mission concept.
Oh, okay.
Yeah. But it is really designed to look at the tectonic and impact history of the planet. And so, as we were just saying a minute ago in the answer to Will's question, an impact is a possibility. David's mentioned Theia, the Mars-sized object that we think collided with the Earth and generated the moon. Possibly an impact. That impact with the Earth may have, to some extent, had an effect on Venus. Although I doubt it. The distances are big enough that I think for any effects on the rotation of Venus, what we've just been discussing, whether it was due to an impact with another body, I think that would have had to have been something separate rather than anything to do with the Earth and Theia. And maybe Veritas will give us some insights into that down the track when it finally flies and we get some really detailed data. What I'm wondering is whether the Veritas mission is going to be modified to carry an airship with it so it can drop down into the upper atmosphere of Venus and have a look at, see what's there, whether the phosphine is actually coming from living organisms or not.
I'm getting very excited, Fred, because we've got helicopters on Mars, airships on Venus, submarines on. Now, where were we going to send the submarine? I can't remember. But these are all concepts I know. But no, the helicopter is really going to happen. But it's very exciting, and the more we find out, the more that we want to know. We want to prove these theories about various aspects of our solar system, and we'll get there eventually. It's just time. It's time, and everything's got to sort of fall into place properly, and keep your fingers crossed, I guess.
Yeah, that's right. We really need to live a couple of 100 years to see all these missions, take shape and watch them progress, especially for once the outer solar system, where you're talking about very long journey times. But that's not really on the agenda at the moment.
No. Fair enough. All right, David. Hope we managed to fill in some blanks for you today as well. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Thanks for listening to the Space Nuts podcast, and thank you to our patrons for supporting us with a few dollars every month. And if you would like to do that, there are a few ways. You can do it through our main distribution platform, Acast. There's a donation option there. You can do it through Supercast, which is where patrons can sign up for package deals and get multiple podcasts for a low monthly fee if you desire. Or you can go to patreon.com/spacenuts and sign up for as little as $3 a month. That's $3 US. And that's all there is to it. Now, it's optional. It's not absolutely and utterly something that we are going to ever make you do. It is totally up to you. And if you do that, we are ever thankful, but it's optional. You do not have to. But to our patrons, thanks as always for supporting us. Of course, you get benefits as a patron. You get bonus material. You get an ad-free version, and you get it early. which is one of the benefits of, or a few of the benefits of being a patron. Now, Fred, we've got a few more questions to knock over, so let's get straight into them. And yeah, let's hit you with the next one.
Hi, Andrew and Fred. It is thought that the asteroid 16 Psyche is an exposed iron core of a protoplanet. I would like to know if the upcoming Psyche probe will determine that. And is it possible that some, if not most of the debris that makes up the asteroid belt is part of the outer shell of this planet? Thank you very much. Love your show. Looking forward to hearing more.
Okay, thanks for your question. Don't know your name, but that's okay. The substance of the question is asteroid 16 Psyche may be an exposed core of a protoplanet. Yes or no, Fred?
It is thought to be exactly that, yes. 16 Psyche is always close to my heart because when I did my master's degree 100 years ago, researching the orbits of asteroids, or minor planets as we call them then, 16 Psyche was the first one that I did observations of. It's a well-known asteroid, but yeah, it's good stuff, a lot of fun. Sort of. Observing with telescopes in minus 15 or 16 degrees Celsius in winter in Scotland, if you could call it fun. It was in some ways. Anyway, 16 Psyche is what's called an M-type asteroid, and the M stands for metal, I think. It's basically made of iron. And that comes... the determination comes partly from its mass. We can measure its size. We know its mass. That gives you its density. It tells you that it's made of iron. But you also have radar observations made from Earth, and that they too essentially speak of an iron-nickel composition, exactly like some meteorites that we see, iron-nickel meteorites, and they, if you've probably seen these in museums, Andrew, an iron meteorite sliced through, and it just looks like a lump of iron. It's kind of slightly dull in colour, but basically shiny. And we think that's what Psyche might look like. Really interesting to imagine the cold iron core of a protoplanet that has been exposed perhaps by a violent collision with some other objects way back in the early history of the solar system, although not early enough to prevent the formation of what we call a differentiated protoplanet, one where the heavy stuff has sunk to the middle. So some sort of collision, it strips off the outer crust of the protoplanet, leaving an exposed iron core. And that is why Psyche is so interesting, because certainly interesting enough to have its own space mission. And this is one that is not in the decades ahead. The launch is in 2 years' time, planned for August 2022, and we expect the spacecraft to go into orbit around Psyche early in 2026. So there's a good chance that you and I will be still talking about these things by then. So hopefully we might get some news directly from 16 Psyche, maybe even images of what must be a remarkable looking object. If the radar observations tell you that it's got an iron-nickel surface, then it must be really quite spectacular to look at. And it's great that this spacecraft, which is called Psyche, as our listener has said, that it's actually been approved. It was approved back in 2017, I think, and is now well on its way. Just one other thing about the mission, Andrew, that's interesting. It uses solar electric propulsion. So that means basically solar panels generating electricity, which will accelerate plasma from the exhaust of the spacecraft to give it the orbit changes that it needs, the orbital adjustments, mid-course maneuvers, all of that sort of thing will be done by solar electric power.
Isn't that clever? I love it.
Great stuff, yeah.
It's a great idea. Now, just one thing that I wondered as a consequence of the question, and I'm going to sound like a blonde myself here now. What exactly is a protoplanet?
Yeah, so it's what we think, planets basically emerge from. It's this multi-layer process. You start off with a cloud of gas and dust. It collapses under its own gravity. The central part collapses so much that the pressure goes up and you get nuclear processes kicking off. That becomes the star. But the debris, the dusty debris, forms, along with residual gas, forms into a disk. And the dust particles stick together by actually electrostatic forces are thought to be the initial things that stick dust particles together. But eventually it's gravity. Things build up to bigger and bigger objects. They collide with one another, so they get smashed up, but then they, basically aggregate again. And you wind up with protoplanets, which are significantly bigger than something called planetesimals, which are the forerunner of that. These are smaller objects. And protoplanets are almost like planets themselves, but smaller. And by almost like, I mean that they are, like we've just been discussing, differentiated into the different layers as gravity pulls the iron down to the middle. Because, of course, it's molten, because you're talking about very high temperatures as a result of the collisions. So a protoplanet is what will eventually become a planet when it accretes more material.
So 16 Psyche is obviously never going to do that because it's been bumped out of whatever orbit it had and is turned into an asteroid.
It's been smashed up. And actually, that reminds me of the second part of our listener's question. Is it possible that some, if not most, of the debris that makes up the asteroid belt is part of the outer shell of this planet? Certainly some of it will be, probably not most, but certainly some of that would be debris from whatever Psyche was before it became a metal asteroid.
There you go. All right. Let's move on to our next question from Andrew.
Hello, Andrew and Fred. This is Andrew Mitchell here from Melbourne, Australia. I was very interested in your discussion about light's journey from the centre of the sun to us. As I understand it, a photon gets absorbed and re-emitted many times, maybe millions of times, on its way to the outer atmosphere of the sun before it comes to us on Earth. But is it really one photon that's making that whole journey? I don't think so. It's not the same photon that gets absorbed and re-emitted. That energy gets converted into energy within the atom that it bumps into, and then it's another photon that starts. I was wondering what you think about that perspective on light's journey, that it's actually different photons. Thanks. Love your work. Bye.
Thanks, Andrew. And just keep an eye on your bird, because I know Muscat is prowling around at Fred's place and probably heard that and is on ready alert. Yeah. I could hear Andrew's bird chirping in the background, and I even heard it ding a little bell, I think.
Yeah, sounds good. Yes, Muscat does have a bell for exactly that reason. Look, Andrew Mitchell, our questioner, is absolutely right. I kind of glossed over that. It's not the same photon. It is exactly as Andrew says, the centre of the sun. In fact, I think they start off as gamma ray photons, very high energy photons, and it interacts with atoms and are re-emitted, and gradually their energy becomes lower. I think I said, I pulled this number out of the air when we spoke about it last time, about 1 million years for the journey, and I've certainly heard that number before. But I would refer Andrew to a really nice piece, which is actually on the Goddard Space Flight Center. It's a NASA webpage. Just Google Journey of Light, and it's an article by Karen Fox, and that gives some lovely graphics, but a bit more detail on how light gets from the center of the sun to the edge. And there is a revised estimate for how long light takes to travel through the sun's years, and the sun's different layers, and it's 40,000 years. So not 1 million years, but still longer than you might expect for what starts off as a gamma ray photon emitted by a nuclear reaction in the center of the sun to bounce its way, being re-emitted as a different photon, as Andrew says, right to the surface and to shine. 40,000 years, it's quite a long time. So yeah, check out the Journey of Light website.
Very good. Thanks, Andrew. And our final question in this episode comes from Barry.
Hi, guys. I'm Barry from the East Nuclear 5 in Scotland. Fred will know exactly where that is. This week's episode really got me thinking when you discussed the possibility that our solar system might once have had a second star attached to it. It got me wondering about the impact on the orbits of planets and on the conditions of those planets when there's a second sun. I was thinking that for a planet orbiting one or both stars in a binary system, you'd expect there to be constantly changing gravitational forces on it, and it constantly being pulled closer to one or other of the stars, or to both of them. The big question for me is how significant those changing forces and movements would be, and whether they might lead to constantly changing conditions on the planet, and so maybe even affect the potential for advanced life developing. I would guess it's a complicated equation, and I'm sure there are more unknowns than knowns. I'd love to hear your thoughts on it all. Thanks, guys, and thanks for a great show.
Thank you, Barry. And I might just point out that I've done a fair bit of family history research, and a significant element of my ancestry is centred around Fife in Scotland. So, I'm very excited to have connected with somebody from Scotland, even as is now. But, great accent too, by the way, and I could even understand him, Fred.
Well, the East Nuclear 5, Barry's absolutely right. I know it well. In fact, if there is a spiritual home that I have on this planet, that's where it is, because that's where St Andrews is, where I had a fair bit of my education. And of course, I might add that one of my daughters lives in Fife still. So
how about that?
Yeah. So we've got connections there too.
Well, I have to go back a couple of 100 years to connect with my family in Fife, but yes, that they did originate there, and as you know, through one branch of my family, which is very exciting to discover. I always thought I had Scottish blood.
Well, that's right. Well, you've got that Scottish chip on your shoulder, which I'm sure I have too. That comes from Scottish origins.
I also don't like spending money, which obviously it's in my blood.
Lovely to hear Barry's accent, a Fifer, and a great question as well about the idea of what happens with the planets of multiple stars. And this has actually been studied in quite a lot of detail, by the theoretical people who model the gravitational influence of things of this sort. I think there are already examples both of planets orbiting one star of a binary system and of planets orbiting both stars of a binary system, which are two very, very different scenarios. Exactly as Barry says, you've got constantly changing gravitational forces. It would result in some tendency towards instability, you would imagine, in the orbit of a planet. But you could find situations where where there are resonances between the various orbits. If you've got a binary system, what that might do, by that I mean a pair of stars orbiting one another, that might impose a particular orbit on the planets of one or both of the stars that might result in stable situations. So I'm not an expert on this, but I know people have worked on it, and the possibilities are there that there will be scenarios where we do have planets orbiting multiple stars. And so exactly as Barry says, how does that affect the evolution of life? You would think it might be quite disruptive. I mean, one of the reasons why we believe life emerged to the form or to the level that it has on our own planet is because of the stabilizing influence of the moon, because the moon stopped the Earth from changing its axis of rotation over time. And I think if you can find stable situations where you've got very, very long periods with climates, fairly constant climates, which we have had on our own planet. The climate does change. We know it's changed over time, but the changes are relatively slow, at least until now. So that suggests that maybe it wouldn't be completely detrimental to life to have multiple stars about which your planet is orbiting. And then you can, flights of fancy of multiple sunrises and sunsets and things of that sort. It's all great stuff. It's worth chasing up, Barry. If you get the opportunity, just have a look at planets of multiple stars on the web. And you probably find all kinds of interesting bits of information that relate to what we've just been talking about. But thanks very much for your question, and thanks for phoning it in too. It's very nice to hear the Fife accent again.
Yes, it's lovely. And I suppose he got the idea from our sun having once had a binary.
Once had a second star, that's right.
But they weren't close together like he's talking about. That's
right. They were probably a very, very long way apart. I can't remember the figure. We talked about it a couple of weeks ago, but it was a widely separated binary system, which we know things like that do exist in our part of the galaxy.
Okay. Thanks, Barry. Love the question. And thanks to everyone who contributed to this week's episode. Really do appreciate it. And, of course, if you do want to ask questions, we're more than willing to accept them. The truth is we don't get to all of them these days because we get so many. So we kind of handpick them and that's just the way it has to be. So no disrespect. We just can't get to them all. Absolutely. That's why we dedicate shows to all questions to do a bit of a catch up on the many that we do get. But we do appreciate it. And you can certainly record your question via our website, spacenutspodcast.com. Click on the AMA tab if you've got a device with a microphone. It's really that simple. Just press record and away you go. Who are you? Where you're from? What's your question? And it will be recorded and we can do what we did today and put it on the podcast. Love to hear all the different voices from all over the world. And that brings us to the end of another episode. Fred, thank you again.
Oh, it's a pleasure, Andrew. Anytime.
How about next week?
Yeah, I can probably put that in my diary. Yeah. Okay, sounds great. Thank you, Andrew.
All right, we'll catch you then. That's Professor Fred Watson, Astronomer-at-Large, part of the team here on the Space Nuts podcast. And from me, Andrew Dunkley, thanks again for listening. We'll catch you on the very next episode.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.